In this video, I want to discuss some of the more theoretical applications of spectral sequences. While these sequences, like the Serre spectral sequence and the Atiyah-Hirzebruch spectral sequence, allow us to carry out computations that would be impossible otherwise, they can also be used to prove powerful results. For example, given a sphere bundle, we can actually use the Serre spectral sequence to derive a long exact sequence in cohomology different from the one induced by the bundle itself, called the Gysin sequence. After I describe this sequence, I'll also give an alternative proof of the 5 lemma. Although it's not too hard to prove just by diagram chasing, I think it's interesting to see how easily it falls out of a spectral sequence argument. The first application I want to discuss is obtaining the Gysin sequence from the Serre spectral sequence. Then say we're given a sphere bundle E over M. Remember that when we say sphere bundle or vector bundle, we're talking about the fiber of the bundle, so in our case the fiber is given by some k-sphere. We're going to see that if we have such a bundle, then we get a long exact sequence of this form, called the Gysin sequence. If you look closely at the indices, you'll see that this is a very different long exact sequence from the regular sequence in cohomology induced by a fibration. For the most part, I'll only be discussing the theory behind this long exact sequence, but in nice settings, the maps in the sequence have very physical interpretations. For one thing, the map pi star is the usual pullback map, which, if you're working with manifolds, notice that our base space is M, not the usual X, can be thought of as pulling a tangent space backward along a smooth map. In fact, in the context of tangent bundles, we can use our manifold structure to define differential forms and integrate them along the fibers of our bundles. In this way, we can define what's called a push forward, denoted pi lower star. For this reason, some authors will write pi lower star for the map between Hn of E and Hn-k of M. However, in a general topological setting, this push forward can't be defined at all, so I'll leave this map unlabeled. Now, our fiber bundle induces a co-homological Serre spectral sequence with this E2 page. Again, the package I'm using to typeset these spectral sequences won't allow me to use k as a dimension, so I'm setting k equals 3 just to draw the E2 page. For arbitrary k, however, you'll see that you get only 2 non-trivial rows, one in dimension 0 and one in dimension k. Then the E2 page will be the same as the EK page, at which point we get differentials pointing k down and k plus 1 to the right. It's important to note at this point that this is where the spectral sequence collapses, since the differentials on the EK plus 1 page and further will overshoot the bottom row. Then the EK plus 1 page is the E infinity page, meaning we get extension problems. By sparsity, we actually only get one extension problem for each cohomology group of E, since there will only be at most 2 non-trivial groups along each diagonal. Here are 2 such extension problems corresponding to Hn of E and Hn plus 1 of E. These short exact sequences are actually related to each other. It's a basic fact in homological algebra that if you have 2 short exact sequences, one ending in the kernel of a map and the other beginning in the co-kernel of the same map, then you can splice the sequences together. Hence we obtain the Gysin sequence. Notice that we didn't have to evaluate any of the differentials in our spectral sequence. All that mattered was that we had convenient extension problems on the infinity page. Now, I did implicitly claim at the beginning of this section that the map between Hn-k of M and Hn plus 1 of M is given by taking the cut product with the class E in Hk plus 1 of M. Now I'll show why this is true. Remember that we have a single generator in Hk of Sk, which I'll call alpha. Notice that the image of alpha under the differential dk will be a class in Hk plus 1 of M, and furthermore, this class will generate the image of dk. I'm going to call this class E. For historical reasons, this class is referred to as the Euler class, and it plays a very central role in the theory of characteristic classes and obstruction theory. Now, the differentials in a Serre spectral sequence satisfy something called a Leibniz rule, meaning that we know how the differential acts on cut products. In particular, if we're looking at a product of 2 cohomology classes and at least one of the classes lies in even dimension, the differential will behave like a regular derivative, giving the following formula. Here I'm assuming without loss of generality that HL of M is generated by a single generator since it simplifies the argument. But no matter which generator AL you consider, you'll get this formula. If you look at the EK page, though, you'll see that dk has to take everything in the bottom row to 0. So in particular, we have that dk of AL equals 0, meaning the formula above reduces to dk of alpha AL equals E AL. Then the claim follows. I know most of the examples I've shown in this video and others have involved the spectral sequence, so I wanted to move away from it for this example. The 5 lemma is a well-known and basic fact from homological algebra, and it's pretty useful when looking at long exact sequences induced by fibrations. Of course, there is a slightly stronger result, sometimes referred to as the 5 lemma also, but I'll just be covering the version where we have 4 isomorphisms. Typically, this result is one of the first introductions to diagram chasing and is proven in this brute force fashion. However, I thought it would be interesting to show that we can also prove it using the spectral sequence of a filtered complex. Just as a reminder, here's the statement. If we have a commutative diagram with exact rows such that the outer 4 maps are isomorphisms, then so is the central map. Since we only have 2 rows, it's not hard to add extra zeros to incorporate the rows into vertical chain complexes. Clearly, if each column has only the 2 non-zero entries, we automatically have that each column is a chain complex. Then we can interpret the rows as filtration levels of a chain complex. In other words, we've constructed a filtered complex out of the data of our original diagram, so let's compute the homology of this total complex. Note that we can filter either by columns or by rows. Some algebraic details aside, the spectral sequences arising from these two methods have to converge to the same thing, namely the homology of the total complex. If we filter by columns, notice that the E1 page will vanish, since we assume that the rows are exact. Then we know that the homology of the total complex is 0. Now, if we filter by rows, we obtain the following E1 page. Notice, though, that since we assumed the outer 4 maps are isomorphisms, we can simplify this page quite a bit. Notice that the differential D1 points 1 to the left, and none of the higher differentials will connect the 2 remaining entries. Then these must survive to the E infinity page. Since we already know that the homology of the total complex vanishes, the E infinity page has to vanish, meaning H is both injective and surjective.